Hi everyone, I'm Shanto. I'm a third-year physics grad student at the University of Southern California, working in the Levinson Falk Lab. And today I will be introducing SQuADDS, which is an open source tool that hopes to streamline your journey from the Hilbert space to the clean room. This is okay. Okay, so as Mohammed kind of motivated previous to me, in a typical superconducting quantum devices lab, you have a Hamiltonian in mind that you want to implement on a chip. And you usually start with an educated guess, and you simulate it, you update your design, you iterate on this process, and you go to the clean room, measure the device, and only to realize your simulation was wrong all along. And anecdotally, we then just use reality as our simulation. Suffice to say that it's a very costly process. With SQuADDS, you get access to a dense database of validated and accurate simulation results that will help you get out of this loop and you just query for your target design, and you go fabricate and hopefully publish on that. So the problem we're trying to solve is that you have some target Hamiltonian parameters for your exact Hamiltonian, and you don't know what the corresponding physical layout for that would look like. How we go on about approaching this problem is by solving the inverse problem, where you have a physical device whose device design parameters you already know. You measure them and record the corresponding Hamiltonian parameters. Next, you use design tools like Qiskit-Metal to simulate the device. And that kind of leads to another problem where you don't know how to converge your simulation results onto your measured device, or onto your measured results. However, thankfully, this is a more tractable problem. And we know that simulations done correctly with the correct methods, as a bunch of talks kind of mentioned, and with the right hyperparameters, you can always find a validation simulation pipeline, which my colleague Andre Quo does a poster presentation tomorrow talking about details of how this works. So with SQuADDS, we record these validated simulation results in workflows and put that on the database. And our tool, and our open source tool, is a Python package which you can pip install, and the associated database, which is available in Hugging Face. Now I'm going to go over an example use case of SQuADDS that you can use to create the GDS file for a qubit capacitively coupled to a cavity. So the first step is you connect to the SQuADDS database. One thing to note is we build our database in a very modular fashion that allows us to save on simulation runtime and also ensure that the simulation accuracy is very high. And this also has an added benefit where we can expand on our database entries by combinatorically adding each component. So second step, what you do is you tell SQuADDS what are the relevant circuit QED elements for your design, which in our case is a qubit and a cavity with the clock. Then you kind of define what these components are. They take in string parameters that correspond to their corresponding names in Qiskit-Metal, so the Q component names. And yeah, so this is what you do. Lastly, you call this createSystemDF method, which kind of merges all the components that you have defined and specified and creates this unified design for you. And also it creates a local copy, a local pandas data frame object for you that you can do further analysis on that contains the information for both the design space and the corresponding Hamiltonians. You can also use the analyzer object to query for the target Hamiltonian parameters of your interest. For our cases, we're looking at a qubit capacitively coupled to a cavity. There are the qubit frequency, qubit anharmonicity, cavity frequency, cavity line width, and the coupling string G. And we use this find closest method, specifying the target Hamiltonian parameters, and you can also define your own custom metric for this. And the results variable will contain all the information you need to create your GDS file from there. So in this case, SQuADDS comes with some custom Q components that you can use. And we have some wrappers around Qiskit-Metal that kind of helps streamline the process to your GDS file. But nothing about this process is custom to SQuADDS. You can also access the relevant design options parameter from the results variable and do it in a very Qiskit-Metal native fashion as well, if you choose to. The last thing I'll talk to you guys about is the interpolation feature of SQuADDS, where what you're looking at over here is, there we go, are some data points from the database. And let's say you are querying some G alpha, cavity frequency, and kappa that is not pre-simulated already. SQuADDS will, of course, give you a design file that has the Hamiltonian parameters closest to this, but let's say you're not happy with this either. SQuADDS comes with a physics-inspired interpolation algorithm that accurately predicts what the corresponding design parameters should be to your target Hamiltonian parameters. Again, this is long, complicated, and very problem-specific, but it works. To test its reliability, we do some simulation tests where we, again, choose some target Hamiltonian point. SQuADDS gives us a closest design point with those closest pre-simulated design point with the Hamiltonian parameters. It also gives us a point with these extrapolated designs that we choose to then simulate. And as we can see, these interpolated design points are actually very close to what we wanted. We do these tests for various points sprayed around in the parameter space. And in all cases, except for this one, we see that the interpolated design really does work really well. We intentionally have included these circled points because we chose these points intentionally to be outside the convex bounds of our parameter space and also in regions where we had very sparse coverage, so we kind of knew that the interpolation algorithm would not be reliable here. And this is a problem that we can solve as we add more data points to our database. And another thing is SQuADDS gives you some native API where, let's say, if you have the simulation capability, once you interpolate and simulate your design, you can just, with one Python method, just send the data to our database and contribute to our project. So again, as I mentioned, the previously shown interpolation algorithm is very problem-specific. Coming up with physics-inspired interpolation algorithm for arbitrary setups is very complicated. But this is a very good use case for machine learning routines. So first, we want to verify whether there are learnable structures in our database. And as you can see from the 2D UMAP projection, there are actually some learnable structures. Nugraha, actually last March meeting, talked about how using invertible neural network architecture with real MVP coupling blocks repeated in like various series does actually a very good job in extracting qubit design parameters from a one-dimensional qubit frequency target. While this works for qubits only, it only is limited to one-dimensional targets. And since our use case is a little bit more complicated, where we want 4, 5, or 6 Hamiltonian parameters, we have tested this network to not work as well. We did find that a very simple black box multi-regression architecture, such as this multinodal random forest regressor, actually does pick up on the physics of the problem in the sense that it accurately finds the trends that the scalings need to be. But we also have found cases where it overfits to the data. So clearly we need more data and possibly a more sophisticated neural network to solve this problem. So in the present release of SQuADDS, we only have data for trans-1 cross and CPW resonators only. And we only have support for Qiskit Metal as our design tool and ANSYS HFSS as our backend simulator. We're very actively working on these features where we use actually SQuADDS SQuADDS have been used extensively throughout SQuADDS. Just wanted to say that. We are actively using SQuADDS and their arbitrary circuits features so that users can then just give us an exact Hamiltonian and their corresponding arbitrary circuit, and we will give them the corresponding GDS design file. We are also actively integrating support for AWS Palace using the SQD Metal tool that a SQD lab in Australia developed, and maybe if Quantum Pro and Nano Academy tools, if they're interested, we can add support for that as well. And most importantly, we are requesting that if you have some validated designs and measured Hamiltonian parameters for those designs, please reach out to me. I would love to have that and add that to the SQuADDS project. Find me after the talk or throughout this week or shoot me an email. Lastly, I would like to advertise some of the great talks that my amazing colleagues at the Levinson Falk lab have going on this week. Please attend them. And our lab is hiring a postdoc. If you or if anyone you know is interested, please reach out to my PI. And these are some resources for some of the stuff with SQuADDS. And thank you for being a great audience, and I'll address any questions now.